Okay, in section 2.5, we're going to talk about implicit differentiation. We have been differentiating explicitly, and we say that because we can solve, or all of our equations have been explicitly solved for y. It's y equals, for instance, we might have had y equals x cubed. And from there, we were able to take the derivative, okay? But sometimes we won't be able to solve explicitly for y. And so what we'll need to remember is that y is a function, it's a function of x. And we're going to kind of apply the chain rule to y. So since y is not just a single variable, it's a function, over here when I do implicit differentiation, I treat it, like I would an inside and an outside. So if my outside is cubed, then I brought the 3 out front, I subtract 1 from my exponent, then I would need to take the derivative of the inside. The way that we're going to indicate the derivative of the inside is by saying dy dx, okay? Or if you wanted to, you could write y prime, all right? But this is just a notation that says the derivative of y with respect to x, okay? X being our independent variable. So let's look at this one. We've got some guidelines, okay? We're going to find dy dx by implicit differentiation. And again, dy dx is another notation for the derivative, okay? And what we need to remember is that y is a function, x is our variable. Notice here, if we were to try to solve for y, we wouldn't be able to do it explicitly. We'd end up with something like y is equal to plus or minus the square root, okay? And so since we got that plus minus thing going on, that's not, we don't get just one function, so that's not going to work for us. So we're going to try implicit differentiation instead. All right, so first step, we're going to differentiate both sides of the equation with respect to x. So I start on the left side. We've got 2x to the fourth plus 3y squared equals 64. When I take the derivative here, I get 8x cubed plus 6y, and I'm going to follow that y with dy dx, okay? Since y, again, is a function, I need to take the derivative of y. It's inside of that square. And so the way that I indicate that derivative is by saying dy dx. Okay, and then the derivative of 64, since 64 is a constant, is just 0. Okay, and so now I want to go on and solve for dy dx. So any terms that might involve dy dx, I'm going to put them on one side and everybody else on the other. So I've got 6y dy dx equals negative 8x cubed, or dy dx equals negative 8x cubed over 6y. And that's our derivative. We were able to find basically y prime without solving explicitly for y first. Okay, let's look at another example. This one steps it up a little bit. We've got y in multiple places. Notice also we've got here, if we look at this first term, we actually have a product. So we're going to have to use the product rule. Just remember, anytime we take the derivative of y, we follow it with dy dx. Okay, we got a product over here as well. So our first step was to take the derivative of both sides. So I'm going to use the product rule on this term. So I've got my first, which is x squared, times the derivative of the second. So that's going to be dy dx. Plus the second times the derivative of the first. So that's 2x. Okay, all of this is just the derivative of this piece. Okay, plus I need to take the derivative of all of this. So my first is y squared. The derivative of the second, the derivative of x is just 1, plus the second times the derivative of the first, which is 2y dy dx. So this is my first times derivative of the second, plus second times the derivative of the first. I had to bring the 2 out front. We're left with an exponent of 1, and then we take the derivative of the inside, so that's where we get our dy dx. And that's going to be equal to 0. We take the derivative of both sides. Okay, now notice in this one, I've got dy dx in 2 different terms. So I'm going to put those terms together on one side and everything else on the other side. So I've got x squared dy dx plus 2xy dy dx. Okay, I just rearrange the order of these factors. Okay, equals negative 2xy minus, this is a y, minus y squared. Okay, I can factor out dy dx right here. And we're left with x squared plus 2x. And over here we still have minus 2xy minus y squared. Or dy dx equals minus 2xy minus y squared all over x squared plus 2x. Okay, and that's our derivative. Now we could, go a step farther and factor, because I can see in my numerator there's a y that's common, and I can see in the denominator there's an x that's common, but the y and the x won't cancel each other out, so we'll just leave that like that for now. Okay, so using implicit differentiation, again, I'm doing it because I can't solve for y in this. We can't separate that y from sine. Or maybe we could, but it would be a little difficult. We'd have to use inverse functions and all of that, and we don't want to mess with that. Okay, so I'm going to take the derivative, and I'm going to be using a product rule. Okay, I've got this times this. Okay, we've got a constant multiple over there. So we're going to take the derivative of both sides. Okay, my constant multiple is just going to go along for the ride. And I get my first, which is cosine x, times the derivative of the second. The derivative of sine y is going to be negative cosine y dy dx. Okay, so that's my first times the derivative of the second plus the second times the derivative of the first. The derivative of cosine x is just actually this is positive. Okay, the derivative of cosine x is going to be minus sine x, and this equals 0. Okay, so I used my product rule. Okay, this was my first cosine x. This is the derivative of the second whenever I had to use a chain rule. So remember, y is a function. I took the derivative of the outside, so that gave me cosine y. And then now to indicate the derivative of the inside, we say dy dx. Okay? And this is my second times the derivative of the first, equals 0. Okay, our goal is to basically get dy dx on the side by itself. Okay, I'll erase that. We didn't need that. So I'm going to say 4 cosine x cosine y dy dx, okay, and I'll say plus 4 sine y, and actually instead of this being plus, it's going to be minus because of that. So minus 4 sine y sine x equals 0. Okay, well, the only term that has dy dx is this one. So I'm going to move my other term to the other side. So we've got 4 cosine x cosine y dy dx equals 4 sine y times sine x. Okay, and if I want to solve for dy dx, I'm going to divide both sides by 4 cosine x cosine y. So 4 sine x, or rather sine y over sine x over 4 cosine x cosine y. And I think it would be a pretty natural move. Of course, the 4's are going to cancel. And then sine x over cosine x is tangent. Sine y over cosine y would be tangent y. So we could say dy dx is equal to this, or we could even write it as tangent x times tangent y. Okay, questions about that? Okay, good. Alrighty, let's try another one. And this time, notice that the square is on the outside, so I've got to deal with that first. Okay, so that is definitely on the outside, so I'm going to say 2 sine pi x plus cosine pi y, and that's to the first. So we've dealt with the outside because it was just a square. The inside didn't change. Now we take the derivative of the inside. So the derivative of sine is cosine pi x, and then the derivative of pi x is pi. Okay. Plus the derivative of cosine is negative sine pi y, and then the derivative of pi y is pi, and then we would need to say the derivative of y, since y is a function, so we say dy dx, and equals 0. Okay, so we dealt with the derivative of the outside and also the derivative of the inside. Again, we had the derivative of sine is cosine pi x. The derivative of pi x is pi. And you could even say the derivative of x is 1, since that's our variable. So now we're going to take the derivative of cosine, which is negative sine pi y. Okay, the derivative of pi y is pi, and then the derivative of y is dy dx. Okay, so we could distribute this piece to each of our two terms inside of our brackets here, I've got two big terms. And so that's going to give me 2 pi. Okay, here's the 2, and there's the pi, because I'm distributing all of this to this first term right now. So 2 pi sine pi x plus cosine pi y times cosine pi x. Okay, minus 2. I'm going to take this pi. Okay, and I said minus because of this. So minus 2 pi, I've got sine x, or rather sine pi x plus cosine pi y times sine pi y. Equals 0. Okay. And I lost my dy dx. I need that because that's what I'm solving for. So dy over dx, dy dx. Okay. So this is the only term now. We have just this one term that has dy dx in it. Everything else can go to the other side. So I'm going to write this as 2 pi sine pi x plus cosine pi y times cosine pi x. Okay, so that's all of this. All right, equals 2 pi sine pi x. Oops. 2 pi times sine pi x plus cosine pi y times sine pi y dy dx. Okay, so I just moved this term to the other side. So that made it positive. And so now I want to solve for dy dx. So I'm going to divide both sides by all of this, everything except dy dx. So we get dy dx equals 2 pi sine pi x plus cosine pi y times cosine pi x all over. Now we're dividing by this stuff. So 2 pi sine pi x plus cosine pi y times sine pi y. Okay. And so lots of things cancel. The 2 pi's cancel. These are exactly the same, so they cancel. We're left with cosine pi x over sine pi y. So dy dx equals cosine pi x over sine pi y. Okay, what do you think about that one?
A lot of work.
It was a lot of work, a lot of pieces to keep track of. All right, so we're going to try one more. Find dy dx by implicit differentiation and evaluate the derivative at the given point. Okay, so this still has the same meaning. I probably won't get to this next problem right now, but the same thing, except they ask us to find the equation of the tangent line. So, once we have the derivative, then we can find the equation of the tangent line from there. But let's look at this one. We're going to find the derivative. So we get 3x squared plus 3y squared dy dx. Okay, equals, okay, for the 6xy, I'm going to use the product rule, and I'll just use 6 as my constant multiple. X is my first, y is my second. So my first is x. The derivative of y will be dy dx. Okay, plus the second times the derivative of the first is just 1. Okay, we're done with that. And then the derivative of 1 is 0. So plus 0. We don't even have to write that. All right, so now I need to get all of my dy dx's on one side and everybody else on the other. So I'm going to subtract y from both sides, bring it over to the left. I've got 3x squared minus, this is actually going to be 6y, okay, equals 6x dy dx minus 3y squared dy dx. Okay, I factor the dy dx out. And we get dy dx equals 3x squared minus 6xy over, or rather 3x squared minus 6y over 6x minus 3y squared. So what this problem asks us to do is evaluate this at a point. Before, when we've evaluated, we've only had a place to plug in an x value. But now we've got a place to plug in the y too. So for x, I'm going to plug in 2. For y, I'm going to plug in 3, because this is the point we're evaluating at. So we get 3 times 2 squared minus 6 times 3 over 6 times 2 minus 3 times 3 squared. Okay, we get 12 minus 18 over 12 minus 27, or negative 6 over negative 15. And we get what? 2/5, if I did that right. Factored out 3. 2/5.